hope you feel refreshed. And I hope you all had a chance to talk about this magic trick or think of how it might work. So I'm now interested in getting your solutions. This is, by the way, such an awesome way to crowdsource something. Like, if you can't solve a problem, like, ask a whole room full of intelligent people to solve it for you. So I can't wait to hear answers. So how might this trick work? Who thinks they've solved it? Who thinks to have solved it? Okay. Who has an idea how to solve it but isn't sure? Okay. Who thinks it's actually impossible? Okay. Interesting. All right. Who's totally uncommitted and doesn't know? All right. So, so the idea, right, is as follows. Here's the solution. So the magician knows the values of the 5 cards that he gets, so he can instantly rule them out. That reduces it from 125 cards to 120 cards, but that still leaves quite a bit of uncertainty. So it turns out that 5 cards with unique integers can be arranged in 5 factorial ways. That's 120 different ways. So the assistant actually does something very clever. So the assistant hands the 5 cards to the magician in a very particular order that is chosen to encode which of these 120 remaining cards is the chosen one. Does that make sense? So simply in terms of information theory, right, we can see that that's possible. We can see that just by choosing a particular permutation of these 5 cards, we can convey enough information to make a choice between 120 things, and there's exactly 120 cards left to choose. The question is, how do you do this in practice if you want to actually practice this magic trick and do this at a party, maybe the same party where you were going to do the other trick. But so the interesting thing, right, is because the cards are unique, and because there's an implicit ordering, in this case there's integers on the cards, it's pretty easy to figure out a code that makes use of that. So you don't need to memorize. For example, if you had cards with different pictures, it would be harder. You'd have to memorize the pictures, and you'd have to memorize an order over the pictures. But with numbers, it's pretty easy. But you can make this as fancy as you like. Still, this is the trick that makes it tick. All right, but we were going to talk about compression, and the next thing on the cards is a little compression puzzle. So here is a chessboard, and independently if you know chess or if you don't know chess, the game is going to be as follows. I want you to devise a code that communicates the state of one chessboard as compactly as possible to another person. So you can sort of imagine famous chess players often get exiled. You're exiled to Saturn or Mars or somewhere, and you still want to play chess. And again, that same bartender charges a stiff fee for each bit. So you want to make sure that you can communicate your chessboard in as few bits as possible. Now, I want you to think about this. If you like, you can chat with your neighbor about how you might do this. Just to get you started, for those who don't know, this is the starting position of a chessboard. There can never be more pieces than these pieces on a given board, as in there will always be at least that many spaces. But as you go on in a chess battle, some pieces might get taken off the board, which results in fewer pieces to be on the board. Also, some pieces are repeated. So, for example, you have the pawns. There are several of these on the board, but there can never be more than one king or less than one king. So you have some choices in how you want to design your code, but the goal is to get the number of bits required down as low as possible. You have 15 seconds to come up with a code, and then I'm going to solicit answers from you. Okay. 15 seconds, as measured by my very inaccurate clock, are over. And I'm going to ask for answers. Who has an idea? Who has a code for compressing a chessboard? Any code will do. If we're rich, we can afford any amount of bits. But like, how can we just with a series of over there? Excellent. So the answer was we could first encode which of the squares actually have pieces on them. And then for each of those pieces, we encode what the piece is. And because they are differently frequent, we may want to have a shorter code word for some of the more common ones and longer code words for some of the less common ones. Did I quote that right? Excellent. What other ideas do we have? Yes? Interesting, really interesting idea. So here the idea was, well, if we all know the starting position, maybe we can just send the order of the moves that happened in the game that will enable someone to replay those moves and end up with exactly the same position. So this is an excellent idea, but it has two problems. One is there might be some board configurations that you cannot reach through a game, like a chess puzzle. The second drawback might be that somehow I'm not convinced that the code will be minimal. In particular, you could imagine having moves that repeat. So there would be multiple different messages that you can send that encode the same board. Any other ideas? Yes? So the question was, is it possible to use a code word that encodes multiple pieces at once? For example, an entire row. Yes, that's perfectly possible. So for example, you might have a code for an empty row, but the question is that are we expecting that we have a lot of empty rows? Or is that going to be sensible? Yes? Oh, I see. Okay, so this idea was, well, how about we know the total number of figures that we have, and we just iterate through the figures and encode the position where each figure is. That's an excellent approach. The drawback is that it is possible that some pieces are not there at all, so we would have to allow for that. And also, as it turns out, chess has a peculiar thing where sometimes you can end up with more than one figure. So, for example, you can end up with multiple queens because sometimes pieces can change into others. Okay, so I'm going to give you some more ideas if you're out of ideas. So I'm claiming, before I'm even going into this, that this is an AI-complete problem to solve. And effectively, we'd have to model, using machine learning, the best possible way of solving chess in order to do the best possible job at it. And that is because the object of interest is the board configuration, right? And effectively, what we want is the distribution over board configurations. So what we're asking is, what are people everywhere in the world most likely to put on a chessboard, whether through a game or through a puzzle or whatever, so that we can expect that our communication of that particular board configuration to someone else is minimized. So the tricky thing is, there are many ways of assigning such a distribution, right? We could, for example, go and use any of the suggestions to start building a distribution. We could iterate over all of the squares. We could have a code that, for example, determines is there a figure or isn't there. Here it looks like there's a 50-50 chance of hitting a figure or not hitting a figure, at least when all figures are present, right? Because there's 32 squares that are empty and 32 squares that have pieces on them. So that's a coin flip, right? That's a 50-50 chance right there. Then once we've decided if a given square is empty or full, we can decide if it's full, what the figure is that's occupying it. again, it seems like there's a 50-50 chance between white and black. So we can choose the color with the next bit, right? But ultimately, if we want to be better and better at this, we can model what moves people are likely to make. We can model what board configurations are likely to happen, because most likely it's not going to be uniform, and there are definitely illegal or invalid positions of chess that are very unlikely to occur, right? So these are the sort of things that we'd have to take into account somehow. And if we have a fixed code, like the one that I just mentioned, where for each square we encode empty or figure, it is possible to put figures on absolutely every cell. And maybe we want to make this much less likely. Or we could, for example, have a whole board full of kings. Maybe we want to make that very unlikely as well. So somehow the code needs to be context dependent. It needs to know that we've already encoded one king. And we could, for example, use the idea that came somewhere from here to maybe iterate through some of the positions that we know, some of the pieces that we know there's only one of, and then find a way of just encoding the position. There are many such ways of doing it, but ultimately it's AI complete. The better you can model it, the better you can model the whole world's brains at playing chess, the better you will do at a competition of compressing random chessboards. So that's the bitter reality. But luckily, the nice part is that as long as we have access to our machine learning tools and we can model in whichever best way we can what the distribution of our objects is, we will be able to design a code that is optimal for that distribution. And the next thing that we're going to do is I'm going to tell you how to design that code. So in particular, remember that we had the decision tree here, right? And that decision tree kind of mapped between probabilities and code words. And I'm going to show you shortly a very general way of using that in order to construct any code for any distribution whatsoever. But maybe before I do that, I want to quickly mention this. So every code that you design implicitly defines a probability distribution. And that's kind of easy to see, right? So we saw it from, if you think about a 0 and a 1 as a coin flip, right? You can kind of work out exactly how much probability mass there is in for each event that corresponds to that code word. So if, for example, you have the code word 110, it takes 3 coin flips. That means you can work out what the probability of that event is. It's 1/8, right? So if you send a single bit, just a single 1 or a single 0, you know it's 1 bit of information and the probability is 1/2. That is the optimal probability that is implicitly defined by such a code. Now it turns out if we have binary digits and we send those binary digits, we can only really define dyadic distributions, distributions that have powers of 2 in the denominator. There's a way around that, but I just thought of mentioning that. So we can easily go from a code to the probability distribution. But the real winner is going from the probability distribution to the code. And the probability distribution might be something like this. So here is a histogram of English text. It was made by Peter Norwick, who took millions of books on Google Books and decided, and they're all English books, and he wanted to get the definitive histogram of English. And that's what came out. So this is exactly how likely each letter is. E is the most likely one. Sorry if I spoiled it. And really, once we have a distribution, we want to get a code that helps us compress objects from that distribution optimally. And here's a way of doing that. Here's a code over 5 symbols from A to E, and I've written down the probability that each symbol has. So the symbol A has probability 1/10, and so on. Symbol B has probability 0.2, and they sum up to 1. So that's a valid distribution, and if there are no contextual dependencies, I can sort of imagine I'm getting messages that are drawn from this alphabet, and I'm expecting to see letters according to these probability masses. Now, in general, when I get a finite discrete distribution like that, there's a beautiful algorithm called Huffman's algorithm that I can run, and it produces you an optimal code. It's pretty important, but also pretty simple. Here's what you do. You write down the probability for each letter or for each symbol, and you pick the two lowest ones. So in this case, that would be A and C, right? Because A has probability 0.1, C has probability 0.14. These are the two lowest ones. We're going to combine them and add them up. We end up with 0.24. So we remove them from the table, add that back into the table. At that point, the two lowest ones will be the combined node that is now totally 0.24 in mass, and B, which has 0.2. These are now the two lowest ones. So we join them up. We create a new node in the tree. And we do this until there are no nodes left. And we end up with this tree, and it's called the Huffman tree. And we label the edges at random with 0 and 1. There are always two edges because it's a binary tree, and we attach a 0 and a 1 in any way we like. This particular tree gives us a way to have code words for each of the letters. For example, the letter A, the symbol A, will have the code word 0, 1, 0, just tracing from the root of the decision tree to the end. And that's the code word that is the best dyadic approximation to the actual probability. It makes the best possible trade-off. Because the real probabilities, right, are not the ones that we started out with, very sadly. So by writing down these binary digits, we get essentially probabilities that correspond to sequences of binary digits, and they're all kind of related to powers of 2. They're dyadic probabilities. So here, E is encoded with a quarter probability, and C is encoded with an eighth of probability, and that's simply related to the length of the code words. But still, if we're only sending one message, this is the best we can do. This is optimal. We can't do better. Now, if you send a lot of these letters, then this won't be optimal. And you can kind of see why, right? So if you were to have two letters that you send at the same time, even if each single letter were distributed as follows, we can work out what the distribution for each bigram would be by forming the product of the distribution, right? Then we'd have to make a new tree that actually correctly encodes the bigram. And that would then be optimal if all you did was communicate a single bigram, which we might not do. So another interesting property of these Huffman trees is that they're uniquely decodable. So they have this nice property that we saw in the beginning when we had some example codes, that there is never an ambiguity as to which code word is next. And that's simply by the way the tree is constructed, that there will always be a choice that ultimately terminates in one of the letters, in one of the symbols. Question there? I'm not sure I understand the question. Can you elaborate? Oh, I see what you mean. Okay. So the question was, when you look at the code words, it seems like there's a missing one. 0, 1 is a code word that doesn't occur in the codebook. Is that your question? And why is that? And this is related to effectively a price we have to pay, right? And the answer is there are two code words that start with 0, 1. For the code to be uniquely decodable, it has to be such that it cannot doubly encode a letter and a choice between another letter, right? So if we see 0, 1, the decoder will go, oh, great, I've got a 0, so I'm going to go down my tree, and I'm going to be here. And then it gets the 1 and says like, oh, great, we can make some progress here, and we end up here. And then you ask, which letter is it? And the answer is, well, I need one more bit to tell you which letter it is, because there are two possibilities, and it's either an A or a C. So this is why there cannot be an assignment of a letter to that node, because otherwise it would be cheating. It wouldn't be able to uniquely decode the code anymore. It wouldn't know, well, does it stop here and I have my G with code 0, 1, or do I have an A or a C? We wouldn't be reliably able to reconstruct the message. That is an excellent question, by the way. That is precisely why the code is constructed that way. And this property, by the way, is called the prefix property. It means that no code word may be the prefix of another code word. And when that property holds, then you have a nice, well-manufactured code that is uniquely decodable. It turns out it's not required to have a prefix code. There are uniquely decodable codes that are non-prefix codes. For example, you can take this one upside down, and it might not have the prefix property anymore, but it's still uniquely decodable. But prefix codes always exist. You can always relabel your ones and zeros as well. That's fine. There are many codes. The essential thing is the code word lengths. And as long as you can find code word lengths that sum up to 1 in their 1 over powers of 2s of the lengths, as long as these probabilities that correspond to the code words sum to 1, you can find a prefix code that fits the bill. That is always possible. So in fact, sometimes in practice, when Huffman codes are sent somewhere, right, it is actually sufficient to just encode these probabilities, and it isn't required to actually communicate the code words, because you can have a rule of how to enumerate the code words if you just know the probabilities. You can essentially just decide that 0 is always on the left side and 1 is always on the right side. Cool. So, but there's a problem with this whole approach, right? So you know how to make optimal codes for any distribution, but in practice your distribution might be enormous. Because the kind of thing that that we might have is a distribution over videos or a distribution over entire novels. Remember that novel from earlier? So imagine that you'd have to consider every possible novel you can write, say up to a certain length, or even just one page of text. And then you start building a Huffman tree based on your estimate of how likely each page is, right? And it might just be random letters on a page. How likely is that compared to a letter of coherent English text? I don't know. Seems pretty hard to me. So Huffman coding is not going to work in that case. What people did originally was they would take single letters, encode them, and then send them. But that's not optimal for the obvious reasons, right? Also, it turns out that there's all sorts of contextual stuff happening in text. For example, the letter Q is very rarely followed by anything other than U. And that means once you've decoded a Q, that should tell you a lot about what comes next. So you should need very few bits to encode a U that follows a Q, even if your U has a low probability. After a Q, it has a high probability. So there are all these sorts of subtleties, and Huffman coding isn't great at that. But it is optimal, and it has, for small distributions, it's perfect, and that gives you a good way to solve that. But the real way to go is to use arithmetic coding. And arithmetic coding is this absolutely beautiful idea, and it solves all the issues that Huffman coding had, but it's slightly harder to understand and slightly harder to implement. But I'm going to walk you through it. So remember our decision tree from earlier? So turns out we can kind of, instead of having 15 numbers here, right, that we had earlier, we can kind of put one of our other distributions on top. So the way we can think about it is, what does it take to encode a B, right? And we've chosen some ordering of our symbols, and this is the probability of our B. And the answer is, well, we have to go down one of these paths. Let's go down this one. Does that uniquely determine which letter it is? No, still uncertain. We can rule out the C, but it could still be A or B. If we go one level deeper, now we can be sure. This interval is perfectly within the interval of B, and we can be certain that B was the letter that was encoded. Now, we could also imagine that we could have gone down this route, right? So we could have gone down here and encoded 1, 0, 0, and that would still mean a B. Long story short, we have a way of identifying a region on the line from 0 to 1, right? We can split this region into as many little fragments as we like. So any of this fragment here will lie inside the B region and would therefore encode a B. But we can stop actually after just 0, 1, because that's sufficient in order to encode our B. This is the central idea behind arithmetic coding. So what we're going to do is we're going to have a target region, and that means effectively you have to be able to evaluate the cumulative probability distribution. But in practice, you can just think of this diagram, of a diagram like this, where you have an order of your symbols, say the alphabet, and you have different probabilities for each of your symbols, and you then bisect the number line into equal halves until you lie firmly within the region of that's your target. And note that your target region can decompose like so. So now we have two symbols. So we have, say, A followed by C, or A followed by B, and that narrows down the region simply by multiplying the two probability distributions, right? So first, by choosing A, we've chosen this region. Now we put the distribution of the next symbol on top, right? In this case, the distributions are the same. So the split between A, B, and C is the same as the split between A, B, and C here. So a second symbol comes along, and we've now narrowed down the region further. And the question is, again, so to encode the sequence AB, what sequence of ones and zeros should we send in order to encode that particular letter combination? And the answer is, here we're starting from the bottom, right? It'll be sufficient to send 0, 0, 0, 1. And that'll lie firmly within this region and therefore identifies that symbol. Now imagine having an entire text where you narrow down the probability more and more. And now imagine that the probability distribution following the B, for example, is contextual on the B. So it doesn't have to be the same as the probability distribution one symbol ago. It can be different depending on which symbol you have. So you can put a different distribution here from the distribution you put here. So putting different distributions everywhere allows you to effectively have map your distribution over sequences to an interval on the real line. And then all you do is binary chop, 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 and you end up having a code. So for example, BB can be encoded with 0, 1, 1, right? We can stop here because it's fully inside the B. That will optimally or near optimally give you a code for that thing. So the tricky thing, the difference to Huffman coding is we don't need to consider all possibilities. We can throw away everything that doesn't actually lie in our target region or near our target region. For example, if we know the first letter is a B, then we can discard this entire computation here. So the conditional distribution on the first letter, if the first letter had been a C, doesn't have to be computed at all. We don't even have to compute it. In Huffman coding, we would have to form the probabilities of all the bigrams, right? So we would have 9 things to work with here, and then we have to construct a full tree over those 9 things. But here, what we do instead is we take symbol by symbol, and we work out the boundary of the interval, essentially the left and the right half. And after that, we figure out the shortest bit string that lies in that region, and we're done. So this is arithmetic coding, and it turns out this is well, first of all, it's just pretty beautiful, but it's also the best, it's the state-of-the-art way of turning any probability distribution into a code. Now, there are some caveats. So, for example, one cool thing that it allows us to do is we can change our distributions as we go along. So, for example, imagine you're receiving a novel and it's in a totally new language. And you're gradually learning the words, you're gradually learning the grammar. As you receive more and more from this alien transmission, you're gradually getting an idea of which symbols are frequent and which ones are not. At first, you start out uniform, but after a while, you see like, oh, this symbol occurs a lot, and this symbol doesn't so much. And you can change that distribution over time using Bayes' theorem, using normal learning, and at the start of the text, you were perfectly ignorant. By the end of the first page, you already have a pretty good idea of which characters are frequent, which ones are not. And you can take advantage of it by simply choosing your intervals according to your guesses. And as you go along, you get better and better at representing essentially each letter with, on average, fewer and fewer bits. This way, your compression algorithm learns as it sweeps through the text, as it builds knowledge. So the learning happens after each symbol, and after each symbol, you get smarter in encoding and decoding. There's just one catch. The encoder has to do the same thing. So effectively, encoding and decoding are two sides of the same coin, right? So both the encoder and decoder have to have a way of reconstructing the same sequence of probability distributions. So if you start out uniform here, for example, the encoder and the decoder both have to start out uniform, or there will be a miscommunication. If if you see one symbol and you learn something from it, for example, you might learn that, well, if I've seen an A, then I think it's more likely to see more A's. That's not an uncommon assumption to make. We'll hear more about this on Thursday. But essentially then, right, I can choose a distribution that incorporates that assumption. In fact, my prior over how the distribution changes given more symbols is exactly the same thing that has to be shared between sender and receiver. As long as the sender learns the same way as the receiver, we both end up learning the language the same way. So I have my alien language, I'm learning which symbols are frequent, and I'm getting better and better at compressing. The receiver says, like, what is this? Has no idea, but as he or she decodes the symbols, they can build the same sort of aha moments as I had when I was compressing it, right? They're decompressing and like, oh, I see, these symbols are really frequent, so we're going to use shorter code words for these. And this way, you can have a self-learning adaptive compressor. All this is possible with arithmetic coding, and it wouldn't be possible with Huffman coding. This is just one of the many cool things you can do. Another simple thing that might help you understand how this works is imagine you have the number pi, right? So here's pi in binary, and you might already know this by heart. There's a thing, right? People learn numbers by heart. And it looks kind of like coin flips as well. Essentially, the probability of a 1 and a 0 are pretty much equal, but it's a deterministic number. Now, you can feed this into an arithmetic coder where you have 0 and 1 here. You feed pi by sort of going, you sort of start by 1, 1, and so on. So you choose pi as the path through this maze, and you end up with a region. After like 1,000 symbols of pi, you are in a very particular region. And now imagine you take decimal digits from 0 to 9 here, and then consecutive decimal digits here. You will decode the decimal representation of pi. You will decode 3.14159, and so on. So this is an algorithm that turns binary numbers into decimal numbers, if you want. But it's way cooler, and you're all like machine learning people, right? Like, you can turn this, like, you're not confined to uniform distributions. You can do this basis transform for absolutely any distribution you want. And that's pretty awesome. This is how powerful arithmetic coding is. And you now have this powerful with it, and my mic just cut out. But all right. So the interface in Arithmetic Coder is typically with fixed precision numbers. I'm just going to flash this at you so that you avoid the mistakes I made when I first tried to implement it. So definitely use integers to represent your intervals. There are some very cool tricks to avoid cases where you have to decide which side of a boundary you go. There are ways of doing it. There's some pretty good papers. If you're interested in implementing it yourself, definitely get in touch. I'm happy to help and show you all the cool papers. The decoder just needs to implement two things, two functions, and essentially then you can arithmetically decode things. You can have an interface, such as you can do this in Python or Java, in whatever you like, called Decodable, which means you have a method of encoding a given object from your space and decoding it back, and arithmetic coding will sit at the back end. Here's a way of doing this for a uniform distribution. Pretty uninteresting. It splits the interval into equal parts and decodes that way as well. Anyway, details. Happy to talk about it. Happy to give you code as well, but pretty exciting. So arithmetic coding is mathematically optimal, except that the bit where it ends needs a bit of extra care. For example, if you have a sequence and you don't know how long it is in advance, you need to encode the end of the sequence, which often means that people add an additional symbol to the alphabet. They have an end of message symbol. And that's perfectly cool because you can model the probability of the end of sequence symbol. Also, you could just send the length of the sequence in advance using a code over integers. And we've already covered those, right? We can have any sort of code over integers, even codes that range over infinite integers. But the real question is, how should we think about English text? And so here I'm going to show you an idea that Shannon had back in the days. Shannon, one of my heroes, remember? And so here's a newspaper headline, and you have to guess what it is. But the trick is you have to guess it letter by letter. So I'm going to ask for audience participation, and I'm going to ask you by shouting out letters that you think will correspond to, in this case, the first letter. If you get it right, then it will proceed to the next letter, and you can guess what the next letter is. Your goal should be to minimize the number of guesses. I want you to collectively minimize the number of guesses you make. So choose the best guess over which letter is going to be here. So who wants to start? I want to hear letters. T, H, E, R, E, I, S. Huh? Which? E, D, A, Q, S, M, N, O, T, H, I, N, G, W, E, S, D, B, M, B, T. So the count will only increase if we haven't had the letter. So it checks which letters you already have, which letters you already had. L, G, I, W, R. Sorry, what was that? S, K, C, Q, U, I, T, E, I, K, E. Excellent. W, A, S, C, M, what? N, A, B, I, Q. What was it? Sorry? A, I think we had A. V, Z. Welcome to Britain. M, T, L, W, F, E, R, G, B, D, C, Z, X. No, it's really just letters from it's letters from A to Z or A to Z at your option, but there's no punctuation marks to guess. I, S, N, H. Sorry. Still not. Okay, you had 20 guesses. There's still 6 letters to go. E, U, F, I, we had I. P, H, R, I, C, S, N, D, A, E, A, P, P, L, E, I, S, T, C, O, H, A, K, L, what's the L? R, P after C? Be my guest. R. N. D. M. F. C after F. It's getting creative. D. Try the vowels. You haven't tried the vowels. O. U. Y. E. A. B. K. B. V. E. P. L. Q. Z. X. S. E. M. Q. You already had that. G. L. C. R. V. W. H. E. Y. Sorry, I didn't hear. J. No. Ah. There's only one letter left, and it's T. Very British. Last 5. You can do it. Sorry? A. B. P. U. L. T. Excellent. Well done. Okay, so one thing, there we go, easier to see. So one thing that's pretty cool here, right, is that your predictive model of English text allowed you to guess in many instances with just one letter correctly what the next letter would be. This is based on an original experiment that Shannon did, where he subjected, in this case, just one single person to questions like that. But here's the cool part. So effectively, it tells you where your uncertainty is, right? So Q took you quite a while to get, whereas the P was pretty hard, but the hardest one of all was the T after CA. So it's slightly unfair because you couldn't see the previous guesses, right? But still, it gives you some sort of idea of the entropy of English in your brains. But here's a cool thing that we can do. So if we now treat the numbers as a code, right, we could imagine that I'm now writing down these numbers, all the ones and so on a piece of paper, and I'm folding it, and I've made a perfect clone in my split universe of this room. So just before this lecture, there's the same copy of atoms, all of you, in your current state of mind when you first saw this, and I have my envelope, which has the sequence of numbers on it. And I'm there, and I'm going to ask you, and what's the first letter going to be? And you shout out letters, and I'm actually just counting. I'm like, take the first answer. So the first one of you were going to shout out T, and I'm like, yeah, that's right, and I'm writing down the T. And so in fact, you correctly predicted the first word entirely. So I could have just gone with, okay, I know it's 5 ones, so I go with the first guess that comes for each letter. And I happen to randomly sample from you, from the clone of your audience, the first letter. And similarly, I would have cloned everything up to the N, right? Where I know it's the 6th letter that I should wait for. So it's going like, no, 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 no. Yes, yep, it's definitely an N. I didn't know it was an N, but I knew it was the 6th recommendation that was coming from the room. So I'm writing down the N. and gradually I'm reconstructing the entire English sentence from a bit of numbers with a help of this entire room that, you know, in a perfect world we can digitally simulate and just keep in our pockets. So if I have a simulated room, like a digital simulation of all your brains jointly, I would have a pretty good compressor of English, just like that. And the cool thing is that is precisely what helps us with data compression. So if you just look at those numbers, right, they are pretty easy to compress. They are much less, there's just a lot of ones. So I can spend very little, very few bits, or have a very short code word for the letter, for the number 1, and have longer code words for the other letters. But essentially, it will take me quite a few bits to get that T, because of this particular room. But, you know, most of the time, you're pretty good and you're really right. So I can take advantage of that. So as long as I have an encoder and a decoder that can make the same choices, I can use that for data compression. And even if, so in this case, right, I don't even have to do any adaptive learning. So even if I just build a Huffman code over numbers, which does nothing adaptive, nothing fancy, I can build an amazing compressor for English that's as good as humans can make it, simply by having a clone of all your brains in my pocket, which should be easy, right? That's for someone else to solve. And so that seems pretty good. Also turns out this is quite a lot harder in other languages. Here's an example in Afrikaans, but I'm probably not going to run you through it, because seeing how long it took you to get that T, I'm just a little worried. But if I give you the beginning, V, A, S, D, W, H, Z, G, D, K, L, E, B, R, A, I, S, B, D, sorry, V, W, E, G, S, T, S, K, H, G, D, V, sorry, B, no. You tried V. T. That's a good one to try, right? Because it came last time. W? No. A. S. H. D. Z. L. B. E. V. B. We had lots of V's and B's and J's as suggestion, and they're still not correct. M. E. E. R. A. S. W. R. E. A. I. Excellent. So this just demonstrated that this room can do one thing that most compression algorithms can't do, which is to compress two different languages just as well at the same time. In fact, that's pretty awesome. I also think it's definitely getting time for barbecue. I don't know why I'm thinking that right now. So essentially, the other way to go is to build entire models over sequences. And I'm not going to do that today. I am going to talk a little about that on Thursday when we're talking about Dirichlet processes. And I just want to make clear that a lot in this world is really based on sequences, right? There's a ton of it. And for example, DNA is a sequence, right? And this is like the latest viral content. This sequence is so dangerous. If you were to actually create this, it could wipe out like all of Stellenbosch. That's how dangerous this sequence is. All you need to do is transcribe this into a molecule. You get a super dangerous virus out. I don't know why I'm even showing this. I would probably get arrested for this. Then E is a sequence, right? Perfectly deterministic, but looks really random. This, incidentally, is more of a normal file, which is not random at all. And you can kind of, if you squint right enough, you can see that there are patterns and lines sort of going in. This is ASCII encoded, definitely compressible. This, on the other hand, is totally random, and there's no way you will ever be able to compress this. So because it's pure randomness, except if you had some insight that allowed you to recreate that exact random sequence, all bets are off. Nothing you can do will ever make this can ever compress this. That's unfortunately how things are. So the answer to compressing sequences, especially text sequences, is that we need to use histograms, but it's not enough to have one histogram. You need more of them. You need to condition, just as we found out, right, on what the previous letters were. And most likely bigrams are not enough. You need to go deeper. You need to have multiple letters of history. And this quickly adds up to having a lot of histograms that you need to learn. How to do that, we'll see on Thursday. And there's some pretty other awesome stuff that we can do with it. The question is, how deep should we go? How many letters advanced knowledge should you need? Ideally, the whole text, right? But it turns out that actually just having 5 is kind of good enough. And if you add more, then in many cases, it just gets worse again, though there are ways around that. But this is sort of how you would build those probability distributions that help you predict the next letter in a sequence. So I am going to show you some demos, because it wouldn't be fun if we didn't have a demo. So if you have a perfect compressor that takes English text on the one end and produces you essentially a sequence of zeros and ones on the other end, right? Remember that arithmetic coding picture. So if we had that sequence of distributions that is perfect for English text, then we could go the other way and we could simply decode randomness, right? So we could simply go feed random decisions from our random coin flip into here and see what comes out. And what should come out is something that looks a lot like English. In particular, we can first feed our algorithm, say, a novel, and then we can feed it random bits. And it's like, yep, keep decoding, and it'll produce some rather curious things. So for example, here, I've trained a compressor on Alice in Wonderland, and then I fed random bits into it, and it produces English text just as diligently, and it looks like this. I can make this a bit bigger if it's easier. Let me try. I can't see my mouse. That's how bad things have gotten. So this is what text looks like according to a compression algorithm, and it just keeps going. And it invents text just by decoding and decoding, and it keeps learning. So when it comes up with new names, for example, it's likely to use these names again because it keeps learning even from what it fantasized. The same works in other languages. So here's an extract of what Crime and Punishment would have been if Dostoevsky had kept writing it. So, you know, looks pretty legit to me. Like, I don't speak any Russian, but, you know, it kind of looks Russian. The same works for other Unicode texts. So this is trained on a kung fu novel. It is so creative; it actually invents new kanji that don't correspond to currently valid characters. Right, way ahead of its time. Like from the future for the win. Look, it even has these sort of weird dividers that it samples. It's pretty awesome. But of course, Shakespeare is the ultimate test. So here's random Shakespeare, and what comes out is pretty sweet. So after being trained on all of Shakespeare's plays, it comes up with this. And the beauty of it is, as I'm not very trained in literature, that looks pretty compelling to me. And best of all, it's kind of like a giant play that has absolutely every character from all the plays in it. So that's pretty good. And it just keeps going with it. I've tried for ages to have a play like this performed, but somehow I've just not been very successful at that. This is what happens if you train on the King James Bible. Somehow I think there was something divine about the original sequence of bits. Like my random sequence of bits didn't yield quite so divine content, but it's still something you can do. But the best of all is these are random drug synthesis instructions. So there's the Shulgin couple who lived in the United States, and one of their best spare times was they synthesized new molecules that would be essentially hallucinogenic drugs or all sorts of crazy drugs. And they're like, well, no one's ever tried this molecule. How about I put the sulfur group on the other end of the molecule or on the other end of the ring? Like, might do something. So they synthesized molecule after molecule, took them in self-experiment, often with horrible side effects. And they're like, horrible, never again. Now let's put it on the other side. Let's add a carbon group here. And they did this endlessly, hoping to find some very interesting, trippy stuff. And then they wrote a book about it. Like, here's all the molecules we tried, and here's how we synthesized them. And now we're making it even trippier by letting a compression algorithm fantasize what those drug synthesis instructions would be if they had kept going, which luckily they didn't. So in any case, I'm coming to an end, and I'm just going to say there are some fundamental limits of compression, and ultimately we're bound by what intelligence limits us to do. And in particular, an interesting question is, what is the most intelligent compressor that we can build? And the answer is, it's the most intelligent machine learning algorithm we can build. So if you've solved hard AI and you've built the most intelligent general machine in the world, you've also built the ultimate compressor. So that's a bonus in case you want to consider. So that would be most likely a machine that can learn any latent algorithm from data directly. So you feed it any data set, and it would learn a latent algorithm that describes a computable representation, essentially, of that data set. So if you can learn any program, you've built the most intelligent thing in the world. No one knows how to do that yet, unfortunately. It's probably impossible to build simply because of the halting problem, right? Who's familiar with the halting problem? Quite a few people. Essentially, it means that there's no way to determine if a given program runs forever, crashes your computer, or produces a nice result. There's no way to determine. If you run it, you know, it might run forever, but there's no way to statically determine that, at least not with a Turing-complete language. And because of that, if you had a program as a latent representation, you might end up with a thing that will just randomly never terminate. So learning in such a space seems really difficult. It's an unsolved problem. No one knows how to solve it. Oh yeah, this is terrible. There's people walking already. Has any of you already left? All right. I take that as a hint that I need to stop. So anyway, the current best compression algorithm is PAQ. It's an adaptive ensemble of many models, and that's a whole interesting subject in itself, meta-learning and ensembling. Super interesting. Looks a bit like a one-layer neural network, but not quite. There's a whole paper on it. Ask me if you're interested. Super interesting. And my conclusion is, as data is getting more and more, right? I mean, we're having tons of sensors, our hard drives are increasing, we have more and more data all the time. Being smart about our data is even more important. So being able to compress is going to be important because it means we can do more with our data. And as you now learned, being able to compress means actually being able to do machine learning. So machine learning is pretty important. And you can do many more things with machine learning than just compress. There are many more interesting things that we can do. All compression is effectively learning, and more efficient learning means smaller files. So neural networks, incidentally, are terribly data hungry, and they're definitely not real-time, so they're not the answer. There's all sorts of really cool techniques that you should be learning about that aren't neural networks, even though neural networks are cool, that can be used in situations where neural networks just simply can't. And the most intelligent and tractable algorithm is definitely still out there. No one's found it yet, so please help us search. Thank you.